Hello from Chem Help ASAP. We should have music for this video because it's resonance. We're going to talk about what is resonance and see one example where we most commonly encounter resonance. And this is a big deal. We're going to see resonance all over the place in organic chemistry. So let's just jump right into it. What is resonance? Well, resonance involves the delocalization of electron density through p orbitals. And where do we encounter p orbitals? Well, we encounter p orbitals in pi bonds. And we also sometimes encounter p orbitals with our lone pairs. So I don't know if you remember way back when you learned about hybridization, sometimes lone pairs, most of the time lone pairs are in hybrid orbitals, but sometimes they are in p orbitals, and that's an important distinction. Those lone pairs in p orbitals are normally lone pairs in p orbitals because they are next to a pi bond. Well, what do you know? There's a reason that we have to pay attention to whether our lone pairs are in p orbitals or not, is because they can delocalize, they can spread out. So delocalization is kind of this idea of spreading out, and we'll try to spell it properly, spread out our electrons. And of course, when we're talking about things that have charge, spreading out the charge is a good thing. Now, to be careful, the term delocalization is only used in the context of resonance. So if you say delocalization, the person listening to you is going to think you're talking about resonance. So only use delocalized or delocalization in the context of resonance. So where do we encounter this? The most common time that we encounter resonance is when we have a scenario like what we have drawn on the left-hand side of the screen, where we have two atoms, arbitrarily A and B, that have a double bond to each other, a pi bond. Could be a triple bond, most often a double bond, but we need that pi bond. And next to that, coming directly off the double bond, is another atom, C, that has a lone pair. Now C can't be three atoms away. It's got to be right next door to that pi bond. And here's what happens. We're going to spread out the electron density. So we're going to use our curved arrow notation to show how the electrons move. And curved arrow notation moves electrons. So we start with the electrons with the lone pair, and we're going to take this lone pair, this non-bonding pair, and we're going to make a new bond between the B and C atoms. Now, atom B probably has already all the electron density it needs, has a full octet. So a bond to B has to break, and that will be the pi bond. And those pi bonding electrons will become a new lone pair on A. Now, for this kind of electron movement, we use this line with arrows on both ends of it. And here's what we get. Atom A, B, and C, they're still all connected to one another. Atom A now has an extra lone pair, and if it was neutral on the left, it will have picked up electron density, so it'll be negative on the right. And atom C has lost the lone pair, that's become a bonding pair, and it actually will now carry a positive charge. So the left-hand structure, if it was neutral, the right-hand structure must also be neutral, and at least net neutral, though we have formal charges. Now, these are both resonance forms. We've drawn a new resonance form. And resonance forms are simply Lewis dot structures, different Lewis dot representations for the same molecule. You just rearrange the electrons. We haven't moved atoms, we've only moved electrons. So if we looked at these as Lewis dot structures, which Lewis structure would we like better? Well, we like the one on the left because there are no formal charges. And so we say that this is the major contributor. The structure on the right, however, has formal charges, and so we say, well, this may be another Lewis structure, but it's not as good. It's going to be the minor contributor. Now, there are implications between these major and minor contributors, but the big picture is we've been able to spread out the electron density. And this spreading out or delocalization of the electron density allows any charges you have in the structure to be more stable. Now, this particular slide doesn't really highlight this difference, but we'll see examples in videos that follow that will demonstrate how spreading out this charge makes the charge more stable. And this spreading out is specifically delocalization, and it happens through resonance.